Engineering can be said to have been in place as far as the time of pyramids. We could say that the first builder was Imhotep, who built the Step Pyramid in 2550 BC at Saqqara, Egypt. His successors, Romans, Greeks, Egyptians, and Persians, gave to the world some exquisite structures which stand upright till modern date with the help of civil engineering combined with geometry, physical science, and arithmetic. Solomon's Temple in Jerusalem, Roman and Persian road system, Pont de Garde in Aqueduct in France, Pharos of Alexandria, and so many more structures are testimonies of their imagination and talent. The Vitruvius's De Architectura, published in the 1st century in Rome, a 10-volume work which covers measurement, building materials, hydraulics, construction methods, and town planning, is the written proof of their engineering skills in the ancient times. The European engineers of the medieval ages were familiar with a rare knowledge of flying buttress and Gothic arch, which the Romans were ignorant of. Villard de Honicourt's sketchbooks, belonging to the 13th century, reveals knowledge of draftsmanship, mathematics, physical sciences, geometry, and natural sciences. Engineering in Asia emerged in a more urbane way. The techniques of hydraulics, construction, and metallurgy aided in the establishment of advanced civilizations, such as that of the Mongols. The exquisite and magnificently beautiful cities of the Mongolian era left the famous voyager Marco Polo awestruck in the 13th century. It was in the 18th century that civil engineering arose as a completely different discipline, and there were universities and professional societies which were initiated exclusively for the subject. The civil engineers of the 19th century built many grand structures, bridges, roadways, railroads, sanitation systems, highway networks, drainage systems, water supplies, and beautifully planned cities. Big inventions which took place in Scotland and England marked it as the birthplace of mechanical engineering. Everyone is aware of the textile machinists of the industrial age, and the engineers of the industrial age like Sir Richard Arkwright, John Kay, James Hargreaves, Boulton and Watt, and hundreds of others. The British developed the machine tool industry, which gave remarkable motivation to learn mechanical engineering, both in Britain and abroad. The field of electrical engineering began from Alessandro Volta's electric cell of 1800, through the experimentations of Michael Faraday and other engineers, which concluded in 1872 in the electric motor and Gramme dynamo. The electrical facet became conspicuous in the late 19th century in the works of other scientists like Heinrich Hertz of Germany and James Clerk Maxwell of France. Some more important developments were seen in the beginning of the 20th century, when Lee de Forest developed the vacuum tube. Other inventions included the transistor in the middle of the 20th century. By the end of the 20th century, electronics engineers outstripped other engineers of the world. In the industrial works of food, metal, and textile, there were different types of use of chemicals. Chemical engineering developed because of the use of chemicals in the manufacturing process, and production of chemicals in large masses was required. The project and functioning of the industries became the job of a chemical engineer. What is engineering? The term engineering could be defined as the application of science to the finest alteration of natural resources for the use of society. The Engineers' Council for Professional Development in the United States of America define it as the ingenious use of scientific principles to develop or structure apparatus, machines, manufacturing processes, or works exploiting them individually or in amalgamation, or to build or function the same with full understanding of their design, or to predict their activities under precise working environments, all as respects an envisioned job, economics of procedure and protection to life and possessions. The British, however, define it more slackly as assembly or manufacture of engines, machine parts, and machine tools. Connected to engineering is a wonderful body of exceptional knowledge. Groundwork for specialized practice comprises a lot of training in the implementation of that knowledge. level of engineering practice are upheld through the hard work of proficient societies, commonly structured on a national or regional basis, with every member conceding an accountability to the community over and above accountabilities to his company or to other members of his society. A scientist has the know-how knowledge, whereas an engineer has the knowledge to do. A scientist enhances the stock of proved schematized understanding of the tangible world. The engineer brings this understanding to bear on concrete difficulties. Engineering is grounded primarily on chemistry, physics, and mathematics, and their leeway into thermodynamics, solid and fluid mechanics, materials science, systems analysis, transfer and rate processes. In contrast to the scientist, an engineer is not free-willed to pick the issue that is of his interest. He is required to give solutions to these issues as they come up. His solution should placate the contradictory necessities. Normally, proficiency costs money. Security enhances intricacy. Enriched presentation upsurges weight. The solution of an engineer is the finest solution, the final result which, considering much aspect, is most anticipated. It might be the most trusted in a certain extent, the humblest which will gratify specific safety necessities, or the most effectual for a given cost. In most of the engineering issues, the social costs are vital. Engineers apply two kinds of natural resources. Energy. Important sources of energy include fossil fuels, petroleum, coal, gas. Others are sunlight, falling water, wind, and nuclear fission. Materials are valuable for their properties, their lightness, strength, durability, and ease of fabrication, their chemical, electrical, or acoustical properties, their capability to insulate or conduct. As most resources are restricted, an engineer should concern himself with the frequent improvement of new resources and the effective consumption of prevailing ones. Main branches of engineering. To speak of engineering as one subject would be vast and never-ending, which is why the discipline has been divided into various branches, all of which have aspects which are unique in themselves, and an engineer could select either one to pursue his studies in. To begin with, an engineer could be trained on one subject, but as the career progresses, other disciplines of engineering could be introduced. Engineering has been categorized in four main branches. Chemical engineering. Chemical engineering is the study and practice of altering substances in huge quantities for the palpable development of the human situation. Such alterations are implemented to create other beneficial substances or energy, and stay at the heart of massive sections of the electronic, petroleum, chemical, and pharmaceutical industries. Chemical engineering is different from chemistry mainly because it emphasizes on huge scales. The description of huge is somewhat random, but is set mostly by the scale of beneficial commercial manufacture. Characteristically, this scale varies from drums to tank cars, while the chemist is mostly alarmed about sizes fluctuating from ampoules to beakers. Electrical engineering. Electrical engineering is the division of engineering which is concerned in know-how of electricity, particularly the design and implementation of circuit board and apparatus for generation of power and circulation, machine regulation, and communications. Mechanical engineering. The discipline of engineering which deals mainly with the commercial implementation of mechanics and with the manufacture of machinery, tools, and their products is known as mechanical engineering. Civil engineering. Civil engineering is the oldest form of discipline in engineering. It deals with the built atmosphere and can be dated to the first time when a person made a roof over his or her head, or placed a tree trunk crossways a river for easy crossing of the river. It is a division of engineering which is concerned with designing, building, and maintaining of the physically constructed works like buildings, roads, dams, canals, houses, bridges, and others. Besides these four main branches of engineering, there are a few other disciplines of engineering which exist. Going back to the ancient times, mining and naval engineering were the main divisions of engineering. There are other branches of engineering which are at times considered as main branches, like computer, manufacturing, corrosion, aerospace, agriculture, acoustical, textile, software, petroleum, instrumentation and control, biomedical, nuclear, audio, automotive, electronic, geological, biosystems, systems, materials, industrial, and architectural engineering. The traditional fields and new specialties are amalgamated together to form completely new branches of engineering, like earth systems engineering, and management comprises of a vast range of areas of subjects, like environmental science, anthropology, ethics, philosophy, and engineering studies. An emergent area of implementation will generally be described momentarily as a variation or subdivision of current disciplines. There is often gray area as to when an agreed subfield permits grouping as a new branch. One main pointer of such occurrence is when main universities begin to institute sectors and programs in the new field. For every field, there is a certain connection specifically in the areas of implementation of fundamental sciences to their branches, like chemistry, physics, and mathematics. Practice. Someone who practices engineering is referred to as an engineer. All who have been licensed to practice might have more professional designations like incorporated engineer, professional engineer, designated engineering representative, European engineer, and chartered engineer. Methodology. The engineers apply sciences and mathematics to find solutions for problems or to better the status quo. It is crucial for an engineer to have the understanding of applicable sciences for their design projects. This helps them in learning about new things all through their career. If an engineer gets numerous options, he measures the consequences according to their merits and selects the best according to the requirement. The main job of an engineer is to recognize, comprehend, and construe the limitations on a particular design to get successful results. It is normally not sufficient just to craft a technically fruitful product. It should also meet additional necessities. Restrictions might compromise of technical limitations, physical, marketability, serviceability, technical confines, output, elasticity for future accomplishments, and alterations. By knowing the restraints, engineers stem stipulations for their limitations within a practical object or structure may be shaped and functioned. A common procedure and epistemology of engineering can be concluded from the historical case studies and observations given by Walter Vincenti. Although his case studies are related to aeronautical engineering, his deductions are transferable to most of the branches of engineering. Problem solving. Understanding of mathematics, logic, science, and economics, and proper experience is used tactfully by the engineers to solve potential problems. By crafting a proper mathematical procedure of a problem helps them in evaluating it and testing the possible solutions. There will be many solutions to a problem, and the engineer needs to calculate the many choices according to their values and filter the best solution as per the need of the problem. Compromising on a particular design reflects low-level design of the engineer, whereas the design which eradicates the problem from its core is the best engineering design. Engineers normally try to foresee how their designs will perform to their specifications before it can be produced on a larger scale. Some of the tests which they put their products to are simulations, stress tests, scale models, prototypes, destructive and non-destructive tests. Testing is important, as they make sure the product performs as per its expectations. Engineering of the ancient era. There are hundreds of monuments and structures spread across the globe which bear testament to the highly accurate work of the ancient engineers. The Brihadiswarwar Temple in Thanjavur, pyramids of Egypt, Pharos of Alexandria, Aztec, Mayan, and Inca pyramids and cities, Great Wall of China, Via Appia, Roman aqueducts, Colosseum, Parthenon, and Acropolis in Greece, Hanging Gardens of Babylon, Teotihuacan, and so many others are proof of superb engineering. The earliest engineer to be known is Imhotep. He was the designer and the supervisor of the Pyramid of Djoser, more famously known as Step Pyramid, at Saqqara in Egypt, constructed somewhere around 2630 to 2611 BC. The Grecians were not far behind, and developed in military and civilian areas. The mechanical creations of Archimedes and Antikythera mechanism, which is the first mechanical computer known, was used to predict eclipses, astronomical and astrological purposes. The two main principles used in the creation of Antikythera was used in the gear trains of the industrial age, and are put to use in the modern world, also like automotive engineering and robotics. There were many complex military machines developed in the ancient age, which were successfully implemented in the battlefields. Roman engineering. The Romans were famous for their endeavors in the field of engineering. Most of their creations were improvements over older ideas, philosophies, and discoveries. It was the Greeks were the first to discover the technology of transporting running water into the city. But since it was not conceivable in Greece, the Romans used the idea to draw water in their cities. The Romans were highly influenced by Greek and Etruscan engineering. Although roads were common during the ancient times, the Romans bettered the design, and the roads which were built by them were so perfect that some of them are still in use today. Their achievements have lived through civilizations, and the praises can be seen in the works of famous authors like Frontius, Vitruvius, and Pliny the Elder, printed proof of their accomplishments. Aqueducts. About 260,000 U.S. gallons of water used to be brought into the city of Rome with the help of 14 aqueducts. Their design and structure matched the modern-day designs of water system. The water was used mostly for the use of the people like sewers and public baths. The aqueducts are 10 to 100 kilometers long and descended from a height of 300 meters above sea level to 100 meters once they reached the city reservoirs. The engineers of Rome used inverted siphons to move the water through the valley if they thought that building an aqueduct would not be a good idea. The aqueducts were built by the Roman legions, whereas the maintenance was the job of the slaves. Roman civilization was the first to have harnessed the power of water. They constructed water mills to aid in the grinding of flour, and also spread their technology in the Mediterranean lands. Building aqueducts required mineral, and the Roman engineers had hydraulic machines to help in mining. Huge vertical wheels, which aid in raising the water, were excavated in the Rio Tinto mines, which belonged to the Roman civilizations. Bridges. Arch was the basic structure which the Roman engineers used to construct timeless bridges. The bridges were made of stone. Pons Aemilius, renamed as Ponte Rotto, is the oldest bridge, made in 142 BC in Rome, Italy. One of the bridges, which is the longest ever to have been built, is Trajan's Bridge, built over the Danube, was made by Apollodorus of Damascus, was about 18 meters above water. Caesar's Rhine bridges are examples of military bridges which were built for temporary use. Dams. The world-famous Subiaco Dam, built by the Romans, is the highest dam to be found. They built about 42 dams in Spain, and one of the famous places where they have built a dam is across the river Sil to expose the gold deposits hidden the river bed. There are many dams which have not been demolished are found in Britain. The dams were normally used to feed water to the aqueducts. Architecture. The Circus Maximus is large enough to be used as a stadium. The Roman architecture is praiseworthy and does not fail to impress the modern-day standards. Another beautiful example is the Colosseum, which is one of the best stadiums built by them. The structure displays curves and arches, which the Romans were famous for adding to their structures. Baths of Caracalla, Pantheon Monument, and Tomb, Baths of Diocletian, have been preserved well. The Pantheon even has its dome intact. These huge buildings were imitated by regional capitals and can be seen across the Roman Empire. The hypocaust, which is a type of central heating system used in the batch, is a technology which is appreciable. This way of heating water was used for smaller villas too. Roads. There are many roads built by the Romans which are still in use. There were different variations used to build the roads. The best quality of road comprised of 5 layers. The first and the bottommost layer was 1 inch thick and was known as pavimentium, while the other 4 layers on top were layers of masonry. Statumen was the name given to the layer right above the pavimentium. It was made of stones bound by clay or cement and was about 1 foot thick. The layer above was called rudens, and as made of 10 inches of concrete. Nucleus was above the rudens and was 12 to 18 inches thick. Next came the summa crusta of silex or lava polygonal slabs, which measured 8 to 12 inches thick and 1 to 3 feet in diameter. The final layer was made of concrete or fitted and planed flint. The Romans believed in engineering any object that hindered the path of the roads, instead of taking the road around it. They constructed bridges if water obstructed, raised causeways, dealt with marshy grounds, whereas the hills were usually cut or a tunnel was made through it. Mining. They were the first among all the civilizations to discover minerals with the help of advanced technology. At sites like Dolichothi in Britain, they used the technology of aqueducts to bring water which would be in the form of a wave and would remove soil to expose the bedrock with signs of gold. Hushing was the same process which they used to get rid of any rock wastes. Hydraulic mining was used at various sites like the Las Medullas, and traces of aqueducts and tanks have been found in the mines used by Romans. Pliny the Elder has described the use of these machines in his works, Naturalis Historia. His works also defined the necessity of dewatering in the mines, which was done by using the reverse overshot water wheels. The site of Rio Tinto has many artifacts which reveal the use of these machineries. Power technology. Vitruvius and Pliny the Elder mention in their texts the use of water wheels by the Roman engineers. The biggest site where water wheels have been found is in Barbegal in Arles. The capacity of the 16 mills found in the area is estimated to be 4.5 tons of flour every day, which was enough to make bread for over 12,500 people residing in the city during that time. A water-powered sawmill was found at Hierapolis, Asia Minor, which is modern-day Turkey. This sawmill is the earliest machine which has been discovered that combines crank with a connecting rod. There are many sites which have been found across the Roman Empire which show the use of these modern machineries, and many sites are yet to be excavated. Egypt. The use of simple yet effective and powerful machines has been seen in the Egyptian civilization. Lever and ramp were common in the process of construction, whereas to solidify the beam of ships, rope trusses were used. Paper was made from papyrus. Although wheel was used for various purposes, chariots came later on. Ancient Egyptian engineers helped in the development of their maritime by building lighthouses and ships. Buildings. The Egyptians built many beautiful temples in the ancient times. Most of them are crumbled, and some of them were lost completely. Most of the eternal place of rest built for the pharaohs stand high. Hatshepsut had massive statues erected of her, and Tutankhamun's tomb was made by cutting rocks in the Valley of the Kings and laid with precious jewelry. Imhotep was the first documented engineer of the Egyptian times. His name appears in the Egyptian pantheon. The Lighthouse of Alexandria is a beautiful example of their lighthouse technology. The lighthouse was constructed in the 3rd century, from 285 BC to 247 BC, and was designed by Sostratus of Cnidus. Alexandria was an important port and was frequented by ships which traded goods with Egypt. Monuments. The Pyramid of Giza and the Great Sphinx are some of the biggest monuments of the Egyptians. The Pyramid of Giza is spread over more than 13 acres in area and is one of the 7 wonders of the world. The caps of the pyramids were covered with gold, while the faces of the statues were covered with polished white limestone. The Egyptian pyramids are gigantic structures made of stone or bricks and were primarily used as tombs for pharaohs. The Egyptians called them Mir, or place of ascendance. The beautiful crimson-hued Red Pyramid of Egypt is the 3rd largest pyramid built by the Egyptians and dates back to 26th century BC. Menkare's pyramid was made of granite and limestone blocks. The Black Priam, from the reign of Amenemhat III, has been completely ruined, but the capstone, or the granite pyramidion, is still preserved in the Egyptian Museum, Cairo. Egyptians were familiar with many techniques which are reflected in their works. They used door lintels, wall and floor veneer, columns, and sill jambs. The Egyptian engineers worked with solid granite, which has baffled the historians. One of the possible ways that they define is the use of lever to move and lift the obelisks that weighed more than 100 tons. Obelisks and pillars. Obelisk is a Greek word, but since the description of the temples and structures has been made by Herodotus, who was a Greek traveler, the word obelisk has been used. The Senusret I is one of the earliest temples which belonged to the 12th dynasty. At Heliopolis, the obelisk continues to stand upright and has a height of 68 feet. 29 obelisks and an unfinished one, which was being built by Hatshepsut for her 16th year as a pharaoh, broke whilst it was being carved out of the quarry, have survived times. The broken obelisk was found at Aswan and reveals the ways of the ancient times about how it was cleaved. It is a mystery to if the Egyptians used kites for their works, but a 5,900-pound, 15-foot-high obelisk was raised vertically with a kite, support frame, and system of pulleys by Maury Garib, Maureen Clemens, and their team. The Egyptians also used ramps, using what they could raise loads applying minimum pressure. Clemens demonstrated by crafting a kite of natural material, strengthening it with shellac. According to their research, shellac had 97% strength of nylon, and in 9-mile-an-hour wind could effortlessly pull a typical of 2-ton pyramid stone 2 courses up the pyramid. Navigation and shipbuilding. The ancient Egyptians earlier had some knowledge of constructing a sail, and they were used just to catch the wind and push a ship or vessel. Around 2400 BCE, the Egyptians discovered that they could sail using the side wind too. There were 5 ships 70 feet long with many sails, which Queen Hatshepsut built. Ships like Khufu solar ship, Abydos boats have survived, and their remains have been found near the pyramids. The Egyptians were the first to use stern-mounted rudders in their time. Other developments. 4th dynasty of the Egyptians has been found to use potter's wheels to design their pottery. Beds, stools, tablets found in the excavations prove that the Egyptians were familiar with the use of furniture. They were also familiar with electric phenomena, which they got from observing the electric fish like eels and lightning. And there are some theories of ancient Egyptian technology which suggest that electric lights were used by them. China. During the ancient times, China also saw many inventions and discoveries. Use of crossbow dates back as far as 2000 BCE. Pottery made out of bronze and iron have been found which belong to the 3000 BC. Makes is obvious that minerals were mined. There are many musical instruments belonging to 3000 and 2501 BC, which show their interest in music. A device which was made of 28 arcs, supported 2 parts of the upper rod, was 3/18 foot of Chinese, while the lower tube was 6/10 in circumference, has been found in sites which date as far as 6th century BCE. There are many bronze castings which are made of complex socket hinges with locking slides and bolts which were found. These devices are umbrellas. Chinese engineers were familiar with the technology of making and using an umbrella. India. At the excavations of civilizations like Indus Valley, well-planned sewage and drainage systems have been discovered. The Indus people had sophisticated water storage and irrigation systems. Artificial water reservoirs date back to 3000 BCE, and canal irrigation systems belong to 2600 BCE. There are many gauging devices found, which were used in construction and angular measurement. Calibration was familiar to the Indus engineers, and was used as one of the measuring devices. The Harappans were familiar with the tides and the shifting course of Sabarmati, which is why the dock found in Lothal is situated away from the main current. The dock is from 2400 BCE. They were familiar with maritime engineering and hydrography. An early furnace excavated at Balakot dates to 2500 to 1900 BCE. The furnace was used to produce ceramic objects. Ovens dating to the time as furnaces have been found at Balakot. Kalibangan site has excavated kiln chambers and kilns with fire. Since the Vedic period, cosmological drawings, constructional plans, and cartographic material have been in use. Unfavorable climates have destroyed most of the evidence yet. Many measuring rods, surveying instruments have been found, which clearly prove the use of cartographic activity. There are archaeological evidences which show the use of plows for agriculture dating back to 2500 BCE. Swords of copper and bronze have been excavated through the Ganges Jamuna Doab region. Engineering during the Renaissance era. The period between 14th and 16th century is normally considered as the Renaissance period. The age is marked by weighty technical advancements like bastion fortresses, printing press, linear perspective in drawing, Florence Cathedral, etc. Leonardo da Vinci and Taccola have represented mechanical phones known and used during those times in their sketchbooks. This era is known to have played an important role in scientific revolution. There were some technologies which already existed, but improvements were brought about in them. Slitting mill, blast furnace, smelt mill, and finery forge are some of the examples. Late 14th century. There were two important inventions in this century, which were the arquebus and musket. Both were different types of guns. Musket was the predecessor of arquebus. While both the guns were shoulder guns, there were heavy arquebuses manufactured too, which needed to be carried by wagons, and carried a ball of 3.5 ounces. 15th century. Technologies which advanced in the 15th century were connected with power and authority. There were three chief inventions which were important during this time: firearms, nautical compass, and printing press. There were more mechanisms which were invented. Some of them were crank and connecting rod. Converting circular motions into reciprocal motions is the main mechanism of a crank and connecting rod, which is also the most crucial mechanism of work. They were first used on water-powered sawmills of the Romans, and the Renaissance period saw more modified use of the system. Printing press. The most important invention of the times is the printing press, which was made by a German goldsmith, Johannes Gutenberg. Printing completely changed the medieval society of Europe. The device comprised of a screw press, which was improved to produce 3,600 pages in a single day, which also aided in the mass printing of books. This increased slowly, and by 1600 there were 200 million copies which could be printed. Parachute. In an unknown manuscript from the Renaissance period, a hanging man clutching a crossbar frame which is connected to a conical canopy has been depicted. This manuscript is from the 1470s. In the Codex, Leonardo da Vinci has presented a modified version of a parachute which has the same frame, but a silk cloth has been depicted in place of the canopy. Dry dock. The Hellenistic period was already familiar with dry dock, but Henry VII of England reintroduced it in 1495, and one was built at Portsmouth Navy Base. Mariner's astrolabe. The explorers from Portugal, Vasco da Gama, Diego de Zambaba, and Bartholomew Diaz all used the astrolabe to navigate their course. The use of the navigation device started from 1481 onwards. 16th century. Floating dock. The most primitive known use of floating dock has been found in an Italian book bearing the title Descrizione della Artificiosa Macchina, 1560, which was printed in Venice. The encompassed woodcut displays a ship lined by two big floating brackets, creating a rooftop overhead the vessel. The ship is drawn in an erect situation, many ropes connected to the structure. Lifting tower. Domenico Fontana used this machine to relocate the huge monolithic Vatican obelisk in Rome. The obelisk weighed 361 tons and was the heaviest block to have been elevated by cranes. 17th century. Newspaper. The society of this period was highly demanding and wished to have fresh and up-to-date information. Writing news sheets with hand and circulating them at this speed in huge numbers was a task impossible. Johann Carolus from Strasbourg was the first to have published a newspaper in German, known in 1605 as Relation. By 17th century, political newspapers were loved by the population, and there were about 250,000 readers in Rome. Air gun. Bartolomeo Crescentio explained about the air gun in 1607 as a device which was armed with powerful spiral spring. Engineering of modern times. The inventions of Scottish engineer James Watt and British engineer Thomas Newcomen escalated the modern mechanical engineering. The growth of machine tools and machines at the time of Industrial Revolution gave way to mechanical engineering in Britain and overseas. Also regarded as the father of civil engineering, John Smeaton was the first self-declared civil engineer. He was an Englishman and was accountable for the designing of lighthouses, canals, bridges, and harbors. Besides being an able mechanical engineer, he was also a well-known physicist. From 1755 to 1759, John Smeaton planned the third Eddystone Lighthouse, where he initiated the use of hydraulic lime, or a form of mortar, which sets underwater, and formed a technique which involved the use of dovetailed blocks of granite in the structuring of the lighthouse. The lighthouse was used till 1877, after which it was moved to Plymouth Hoe and was named Smeaton's Tower. His discovery of what is modern cement is a milestone in history, as it was he who acknowledged the compositional requirements required to get hydraulicity in lime. This eventually led to the discovery of Portland cement. The United States of America census of 1850 showed 2,000 engineers. Before 1865, there were less than 50 engineering graduates in the United States. By 1870, there were about 12 mechanical engineering graduates, and the number increased to 43 every year in 1875. There were about 6,000 engineers in the field of mining, electrical, civil, and mechanical. Until 1875, there was no chair of applied mechanics and mechanism in Cambridge, whereas it was only from 1907 that Oxford got the chair of applied mechanics and mechanism. Germany was a little more advanced and had technical universities much before. The beginning of electrical engineering comprised of the experiments conducted by George Ohm, Michael Faraday, and Alessandro Volta in 1800s. There were other inventions, including that of electric motor in 1872. In the 19th century, the theoretic workings of Heinrich Hertz and James Maxwell founded electronics. Invention of transistor and vacuum tube speeded the progress so much that the students of electronics and electrical outstrip students of any other engineering field. Manufacturing processes at the industries required new processes and materials, and chemicals were wanted at a large scale by 1880. The demand was so high that a complete new industry was made, and was devoted to the manufacture of chemicals in large scale in the industrial plants. The role of the chemical engineer was to design these chemical workshops and procedures. Aerospace engineering is a contemporary word which stretches the subject by including spacecraft. The origin of aerospace engineering can be tracked back to the aviation inventors about the beginning of the 20th century, though the efforts of Sir George Cayley has lately been dated as existing from the last decade of the 18th century. Aeronautical engineering is a subject which studies the designing process of an aircraft. Primary understanding of aeronautical engineering was mainly empirical, with some ideas and abilities introduced from additional divisions of engineering. Joshua Willard Gibbs was the first man to have received the Ph.D. in engineering in 1863 at Yale University. It was also the second Ph.D. to be bestowed in the subject of science in the United States of America. Within 10 years after the Wright brothers flew effectively, there was a lot of development in aeronautical engineering, which could be seen in the World War I aircraft of the military. Charles Babbage has been credited with inventing the first mechanical computer in 1822. The initial meaning of computer was a man who performed computations and calculations, and was used in 1613. Because of inadequate funds, Babbage could not finish his work, and in 1991, the London Science Museum finished his work and added the printing mechanism to the device in 2000. The first personal computer was made by Ed Roberts in 1975, which was named Altair 8800. Released in September of the same year was a portable computer, or laptop, by IBM.